Okay, so this is actually the Lagrangian of quantum electrodynamics. I have already written it and now I'm recording it, so I will highlight the parts which I'm explaining. Anyway, we start from the Dirac Lagrangian here, and then we see that how psi bar and psi transforms, which are spinors in this case. So psi bar, if we transform this, it will transform like this. It will be transformed using this transformation law, and e to the minus iota q theta into psi bar, and similarly psi prime would transform like this. Okay, now we have to see that first of all we have to see that if this is good, or if this is invariant under the global transformation. And to do that we have to transform our Lagrangian, and for transforming we have to use L prime, and we will use the psi bar prime, and for psi bar prime we will use this transformed psi here and here. Anyway, after transforming, we see that globally if we transform this Lagrangian, so it is basically unchanged. So yeah, if we use these transformation laws, so our psi is invariant under global transformation. So now we want to see that sorry, now we want to see that if this Lagrangian is invariant under a local transformation, local transformation. And in order to do that, we will take our theta, and we make our theta dependent on the position. So it will be thetas of x, so this will be a function of position. So now if we do that, if we do the calculations, at the end we will get our normal Lagrangian, but we get another term which actually shows that this Lagrangian is invariant under local transformation. And how to deal with this? So normally if if our Lagrangian is invariant under local transformation, so in this case usually we introduce a covariant derivative, and I think I have uploaded the first two videos of where I derived the Lagrangian of quantum chromodynamics and the Lagrangian of electroweak theory. So yeah, we already have used this technique. So yeah, in order to deal with this kind of thing or invariance, we use the gauge principle, and we introduce a covariant derivative. So covariant derivative have this kind of shape, and now we now we have actually replaced our normal derivative with the covariant derivative. And if we see again, if we replace this and put this again into our Lagrangian, so it will be like this. We will get Lagrangian plus another term. So this term here is actually the interaction terms among the fermions. So the fermions interact with each other too, and here you see that E signifies basically the strength of interaction, and Q is basically the charge, and E and Q is not fixed by the theory. And here you see A mu is basically an auxiliary field or the gauge field. Okay, so after introducing the covariant derivative, we see that we get our original the basic Lagrangian from which we started, and we get another Lagrangian term, which is basically the interaction terms, which is basically the interaction term. Now as we have seen, as we have said, that if we let our theta depend on position, so we will see that if we make our theta depend on position, will it be still local, will it still be good in local transformation? So yeah, we depend our theta on position, and with this psi bar will transform like this, and this will psi will transform like this. And and when we take the derivative of this e to the I q theta and psi, and yeah, basically now psi is also a function of position, and theta is also a function of position, so we will apply the chain rule, and we will get the other terms too, the m term here, and then our interaction term, of course, here. So in the next step we will get our interaction term as usual, and yeah, here this auxiliary field will also transform, and I have not written here the transformed psi bar and psi, because eventually they will cancel out with each other, so I just put a prime over the auxiliary field. Anyway, the auxiliary field or the gauge field will transform like this, and now if we put our transformed auxiliary field, so we will get these two terms, and the second and the fourth term will be cancelled out, and eventually we will get again that Lagrangian that we got earlier here. So yeah, this this covariant derivative, by introducing this covariant derivative, we have saved not only the global transformation but also the local transformation. Okay, anyway, this Lagrangian is not completed, so we need to introduce a kinetic energy term, and for this we will use the electromagnetic tensor, field tensor, electromagnetic field tensor, and that can be obtained by taking the derivative of the for current for potential, and yeah, if we do that, we can get the electromagnetic potential, and by taking the trace of this four momentum, we can get the kinetic energy term, which is quadratic in nature, quadratic in field, and we can also add the mass term, basically, which will have this form. Let's say the mass term, it will be like this: 1/2 m square, yeah, it will be like this, and it will be quadratic in field, and if we do that, and if luckily we know that the photon is not massive, the photon is massless, that is in our favor, that that actually makes convenience for us. But actually, if we had a massive photon, if we had a massive photon, a hypothetical thing, a different world, if we have a massive photon, in that case our gauge invariance would be destroyed. But anyway, we got massive bosons, massive fields like the Z field and the W field in electroweak Lagrangian. So in that case, we introduce new techniques to deal with the massive bosons. Anyway, here we don't need to worry about this thing, because we can introduce that mass term that will be quadratic in the field, but actually we don't need to include this, because experimentally we know that the photon is massless. Anyway, after introducing the kinetic energy term, so this is our complete Lagrangian of the quantum electrodynamics. So this is our complete Lagrangian.